Swayam Prabha. Digital India. Educated India.
In the previous class, we discussed about application of Reynolds transport theorem to derive the fundamental governing equations for fluid flow. Then I introduced you to application of the transport theorem for single particle equations. So, for the mass conservation, we have to consider this parameter beta is equal to 1, and then the transport theorem basically can be written as this, and from mass conservation we know that the rate of change of mass should be equal to 0, and this basically tells us that the rate of change. So, here you should understand the difference here. So, this capital M refers to the system mass, which is 0, but here the small m refers to the instantaneous mass of the particle. So, the rate of change of mass of the particle, what we see is that is equal to the rate of the efflux of the vapor from the surface of the particle. Okay. So, we get this equation. So, here it is important to note that unlike the case of fluid flows, in this case the control volume is not fixed. The control surface shrinks, for example, in case of evaporation. Okay. And in addition, the control volume can be accelerating, rotating also. That does not matter here, while in case of fluid flow, the control volume is always fixed. Now, we will look at the momentum conservation, and first linear momentum, we will consider the linear momentum. So, in this case, so what is the value of beta? This is the velocity of the particle. So, if we plug in this here, we get this expression. So, on right side, what do we have? The force. So, rate of change of momentum is basically equal to the external force. Okay. So, then here if we assume that there is no particle rotation or internal motion within the particle, then we can write the first term as this. So, basically we can take the velocity out and integrate this to get mass. The integral of the volume integral of density times the differential volume is basically equal to the mass. So, that is what we get. Now, here why we are making these assumptions here? No particle rotation. What happens if the particle rotate? We will see that just in the next slide. So, if the particle rotates, then what would be the velocity? See, the particle is translating as well as it is rotating. So, in that case, every point on the particle will have a different velocity. Although all points in a particle move at the same translating velocity, but there is a rotational component also, which is different for different point within the particle. So, that is why here we are assuming no particle rotation. That is the reason why we could treat this term as constant. And also there is no internal motion within particle. What is meant by internal motion? What can cause internal motion? There are different ways in which one can realize internal motion within particles. Typically, this happens if you have a liquid droplet. So, for example, the the external force or the surface force itself can cause a shear. So, let us say I inject a droplet into a flow, then here there is a shear stress, for example, and that can cause the interface to move, and that can cause a velocity gradient within the particle. This is the other way is, if because of any reason the temperature of the surface is not uniform, then we can have surface tension driven internal motion. So, in that case, even if the particle is stationary, it is possible that there is some internal motion, and that is because of Marangoni convection. Okay, because of some reason, if there is a temperature gradient on the surface, then the surface tension is different, and that causes the flow to happen. Okay. There can be other possible scenarios also. For example, let us say you have two different liquids, mixture of two miscible liquids, let us say heptane and ethanol. Then they have different rate of vaporization, their vapor pressure are different. One liquid vaporizes faster than the other. Then what will happen? The liquid which has higher vapor pressure would tend to move towards the interface, okay, and leaving behind the one which has lower vapor pressure. So, this also can cause some velocity, though the magnitude of those velocity, it depends on the particular case. Okay. It may be much lower than the translational velocity of the particle. Okay. But anyway, in this case we are treating the velocity of all points on the particle to be same, and that is why we could take this out, and then using chain rule we can express the first term as this. Next, if we consider the second term, here also we can take the velocity term outside, and then we can assume that the density at the surface as well as the efflux velocity. What is efflux velocity? This is the velocity at which the vapors move in the outward direction. So, and these are same on the surface of the particle. Okay. So, when this will happen, or when this is more possible, when we have a spherical shape of particle. Okay. So, in that case we can integrate this should be yeah. So, we can integrate this and we get the velocity times density multiplied with the efflux velocity multiplied with surface area. Now, what is this? This part. From the mass conservation equation, if you remember, this is nothing but the rate of change of mass. So, we can put this term as rate of change of mass. And now, if we add this one and this one, then this term basically cancels out, and finally what we have is mass time the acceleration is equal to force. So, now here you see we get this expression even if we have the vapor leaving the surface. So, basically the equation, what it tells you, that the fundamental equation remains same whether we are considering a rigid particle or an evaporating particle. Okay. Now, this force is equal to the external force, which can be body force and the surface force on the particle. The body force can be due to gravity or due to let us say if you put the particle in some electric field, then also you can have a body force. And then the surface force, we have this due to pressure and due to the shear stress, as we have done in case of fluid flow equation. So, but at this moment what is important here is to realize that this is the final linear momentum equation that we derive from the Reynolds transport theorem. We consider angular momentum. So, what is angular momentum? Angular momentum is basically the moment of momentum. So, this is your momentum. Now, this is the angular momentum. So, moment of momentum. So, here we are referring to a case where the particle is actually now rotating, and in this case here you can see. So, if we consider any point here on the particle, and this is a distance, because we are already using the symbol r to represent the particle size, I am not repeating that. So, this is the radial distance from the center point. Then here we have a rotational velocity which is equal to this distance times the rotational speed. Okay. So, now in this case what will be the value of beta? This should be angular, specific angular momentum. So, angular momentum per unit mass, which is nothing but this. So, now here why I am writing capital U? Because this is the resultant velocity that we have. So, this is the overall particle translational velocity plus this is the velocity due to rotation. So, now we need to plug in this in the transport equation. So, yes, so this is the particle rotation vector. Okay. So, now if we plug in this value here, we get this expression. Okay. So, I have just replaced beta with this. Okay. So, now this, what does the left side represent? Rate of change of angular momentum, and that should be equal to torque on the particle. Okay. So, then it is if we assume a spherical particle, then we can show that the mass flux from the surface due to evaporation contributes to it does not contribute to torque. So, without going into the detail of the derivation, what we get is this simple expression. So, basically here if you see this part, we have, so this part does not contribute. Now, this part we can simplify to show that the torque is equal to I, where I is the instantaneous moment of inertia about the axis of symmetry. So, moment of inertia times the angular acceleration, that is what we get. Okay. However, if the particle has some, let us say, arbitrary shape, then it may contribute, but usually the velocity, the vapor velocity at the surface is much smaller than the particle velocity itself. However, we cannot generalize, it depends on the particular scenario that we are considering. Usually it is less, but if you have a case, let us say, where we inject droplet into, let us say, some supercritical condition, for example, what happens in a rocket engine. So, there it may be important, we do not know. So, now we will move on to energy conservation for a single particle. So, in this case, what is the parameter beta? The energy, here we are referring E to internal energy. plus the kinetic energy. Okay. So, we plug in this to the transport equation. So, the left side shows the total rate of change of energy of the particle, and according to first law of thermodynamics, this is equal to net rate of heat transfer and work transfer. Okay. So, here the heat transfer refers to the convective and radiative heat transfer to the particle. So, the convention is that if heat transfer is to the particle, it is positive, and in this case work done is positive if the work is done by the particle on the surrounding, by the system on the surrounding. Okay. So, here what does work transfer rate refer to? This is basically the work transfer due to the fluid, the vapor which is leaving the control surface, and the work associated with the forces on the droplet. So, whatever force we have on the droplet, what work it is doing. For example, can it deform the droplet? So, that work we have to consider, but in that case it will be work done on the droplet and it will be negative. Okay. So, now again we will make some assumptions again, that there is no particle rotation, no internal motion within particle, and also that the kinetic energy associated with the efflux velocity. So, the velocity at which the vapor leaves, say, droplet, it does not contribute much to the overall kinetic energy. Okay. Or it is much less than the enthalpy involved in the phase change process, you can say. So, that is why we are neglecting that. So, if we neglect that, then it is possible to show that this equation basically simplifies to this expression, where we have mass times specific heat times the rate of change of the temperature of the particle, which is equal to the convective heat transfer rate plus radiative heat transfer rate, plus we have also the contribution from the phase change. Okay. So, if we have, say, a droplet which is evaporating. Okay. So, finally, here we summarize the equations that we derived using or applying Reynolds transport theorem to a single particle, mass, momentum and energy conservation equation. So, how about the species equation for this case? We did not consider the species equation for the particle phase. So, is it important? The answer is yes, if we are interested in the species, if we have let us say a kind of multi-component droplet. So, for example, diesel or all practical fuels, okay. And if we are interested in the transport phenomena associated with each species within a droplet, for example, what I just mentioned. So, let us say you have mixture of two liquids with different vapor pressure. So, you want to understand the transport of individual species within the droplet, which may be important to derive models for evaporation of those kind of droplets. Okay. In that case, we have to consider the species equation, but here we do not, okay, because our focus is more on the transport of the particles. So, even if that happens, we can use some suitable model for that, okay. But it may be important in some cases. Next, so are we done with the transport equations? The answer is no. Why? Because we do not have these expressions in terms of fundamental quantities. For example, here in case of momentum equation, we need to express this in terms of velocity of the dispersed phase and maybe the carrier phase flow velocity also. So, in case of mass conservation equation, we need to express this in terms of fundamental quantity, for example, particle size. Okay. Similarly, in case of energy equation, we need temperature. We need to express this in terms of temperature. So, that is why we need constitutive relations to close the equations. Now, for that purpose, we need suitable models, okay, to relate these quantities to the fundamental quantities. And now, again we will revisit the conservation equations one by one and see what type of constitutive models exist. So, first let us consider mass conservation again. So, as I just mentioned, so this is the equation for the mass conservation. Though throughout our discussion I was referring to evaporation, but this equation is not restricted to evaporation. That is what I want to highlight here. So, basically this will change sign if we have condensation or evaporation. Okay. So, if we have evaporation, then the rate of change of mass of the particle will be negative. If we have condensation on the other hand, it will grow, the particle size will grow. Okay. But what is of our interest is this part. What is this? This is the mass flux at the surface. That is, what is the rate at which vapor is generating per unit area per unit time in case of evaporation. So, this is what we need. So, the question is, how do we model this? So, for that purpose, we will discuss a very popular model known as D-square law model for droplet evaporation, which was derived by Professor Brian Spalding about 40-50 years ago. Many other researchers further fine tuned it, but the basic model is what we are going to discuss. So, for that purpose, we have to make some assumptions first. Okay. So, you imagine, so what is the objective here is to predict the mass transfer rate from droplets in any application. So, we have hundreds, millions of droplets, let us say in some application in a spray. Now, how do we predict the mass transfer rate? So, for that purpose, we have to first of all simplify the system, and that is what is being done here through these assumptions. So, first we consider a single isolated droplet. You imagine you have a single droplet sitting somewhere in this room far away from any other droplet, and also assume that there is no gravity effect. So, just one droplet is placed in the room. Okay. Let us say water droplet. So, here this dark blue part is the droplet, and you have the vapor which is produced and which the vapor is transported away from the droplet. Then we assume that the droplet shape is spherical, so that we have spherical symmetry around the droplet. It helps to simplify the equations to a great extent, because we know that in this case basically the transport of the vapor will take place only in the radial direction. Okay. Next, we assume that the droplet temperature is uniform, such that the vaporization rate on the surface of the droplet is same everywhere. Then we assume that the air is not soluble in the liquid. We will see later why this assumption is required. And is it possible that, so intuitively you may expect that it is obvious, but it may not be so in some cases. Next, we assume that there are no chemical reactions present, for example, combustion, though we will see combustion later. Then there is no heat transfer due to radiation, and you have a stagnant ambience, that is, the air is not moving. Okay. You do not have any convection also. Even if the droplet temperature is high, there is no natural convection, no forced convection. Okay. Then importantly, the gas phase is in a quasi steady state. Now, this is a very important assumption. So, what is meant by this? So, if you see here, we are going, although our interest is on droplet vaporization rate, we are going to consider the vapor transport mainly. So, we are going to write equations for the vapor transport, which means that we are going to consider the gas phase equation only. Now, the question is the transport of vapor a steady process or an unsteady process? Unsteady, because the droplet itself, the droplet vaporization itself is an unsteady process. However, if we assume that the rate of species transport, what is meant by species here? If you have a water droplet in air, then in the air there are two species, one is water vapor, the other one is air. Okay. So, the rate at which the vapor is mainly transported is much higher than the rate of change of droplet size. So, the droplet basically shrinks slowly compared to the rate at which vapor is transported, as simple as that. So, what is the consequence of this is that we need not consider any unsteady term in the equations. Okay. The next step. So, how do we develop this model? So, again we consider this single isolated droplet, and we define this G term, which is basically vapor mass flux at any radius here r. Again, what is vapor mass flux? The rate of transport of the vapor, how much of vapor is transported across unit area per unit time at any radial location r. This is basically this term. Okay. Now, this means that the rate of the flux at the droplet surface is defined at r is equal to r naught, where r naught refers to the initial size of the droplet. Okay. Now, what is this vapor mass flux at the droplet surface? This is what we are interested in fact. Okay. This is what we want eventually. So, now if we consider the species conservation equation, because there are no chemical reactions in the gas phase, so for the vapor we can write that the vapor mass flux times 4 pi r square. What does this represent? What does the left side represent? The rate of vapor transport, not the flux, we have integrated it. Now, this is equal to constant, that makes sense, right. So, this tells you that this parameter gr dot r square, it is a constant. So, which just simply tells you that as you move away from the droplet, this flux is going to reduce, because flux times total area is constant, as simple as that. So, and you get this equation, because again the mass has to be conserved. whatever vapor is leaving at the surface, that is what is going across any location defined by radius r, that is all. Now, for air, so this is for vapor, but for air also we can write a similar equation. Now, what is meant by this for air? What happens to the air? So, initially you imagine at time t is equal to 0, the droplet is just starting to vaporize. You have air everywhere, and now after some time some vapor is present in air. Now, what happens to the air which is present there? One thing. Second thing is that vapor is moving this direction. So, in which direction the air should move? If you consider now here I am referring to diffusion of this species. So, if you consider, let us say, a container and you separate the region with a diaphragm, and let us say here you have two species, vapor and air, and if you remove the diaphragm, what will happen? They will move opposite to each other, okay, and that is what is happening here. So, the total diffusion flux should be equal to 0, okay. So, but what we see here, but if we consider only the species which is air, there also this equation must be valid, because air is not consumed anywhere. So, now this means that the mass flow rate of air at any radial location should be equal to mass flow rate of air at the surface. Now, we know that air is diffusing in this direction opposite to that of the vapor. This is air. But can air diffuse into the droplet? We have assumed it not to be so. This is the reason why that assumption is there. However, it may not be valid, especially when we have very high pressure ambience. For instance, even a diesel combustion chamber where the pressure is high, or let us say rocket engine combustion chamber where pressure is high or close to supercritical conditions. So, there the diffusion, some diffusion may take place, but here we are assuming it is not there, and this immediately tells us that the flux for air is 0. Again, now what does this mean, that flux for air is 0? So, if you see, when we say mass flux of any species, it has two components. One is convective component, one is diffusive component. Okay. So, the total flux for air is 0, which means that for air the diffusive flux is equal and opposite to the convective flux. Okay. So, because of the vapor generation, the air is being pushed out, but at the same time air has to diffuse in. Okay. That is the reason why the total flux is 0. Okay. But if I ask you, okay, why the vapor is moving out? What causes the vapor to move outward direction? Because of diffusion. But what causes diffusion? Gradient in the concentration of vapor. This is what is Fick's law of diffusion. Okay, Fick's law of diffusion tells us the diffusion flux. Okay. So, the concentration of vapor at the surface is higher than the concentration of vapor far away from it. For example, again if you consider water droplet in the air, then you have to see what is the vapor concentration in air. If you have dry air, then vapor concentration is 0. otherwise some value. But at the surface of the droplet, you have higher vapor concentration, and because of the concentration gradient, the vaporization is actually taking place. And that is the reason why if you put a water droplet here, it vaporizes, okay, even if the water temperature is not equal to the boiling point temperature of water. Okay. This is evaporation which can take place at any temperature below the saturation temperature. Okay. But you imagine the relative humidity of this room is 100%, and then you do the same experiment, that is you bring a droplet and keep it. Will it evaporate? Answer is no, because the gradient is 0. Okay. And that is why we have now we will follow this equation now for vapor, and we will write the vapor mass flux at any radius r is equal to this term. Now, this has two components. One is convective component. The vapor itself is transported due to the bulk motion. Remember, there is no airflow here, but still you have bulk motion of the vapor, and that is what is causing this term. And then this one, this is the diffusion, and in fact we have used Fick's law of diffusion here. So, according to Fick's law of diffusion, the diffusion flux is given by minus density times the diffusion coefficient times the gradient of the vapor mass fraction. Okay. So, here we are using Fick's law of diffusion, which itself is a model for diffusion. Okay. So, now once we get this equation, then we can write it this way. So, bring in this term r square inside, but what is this term g r square? This is equal to g naught r naught square here. So, we can simply use this here, okay, and we get this equation. Okay. Then we can simplify this equation and bring it in this form. So, what are the variables here? The variables are y and r. So, then we can integrate them. So, what is y? Y is the vapor mass fraction, and we have to integrate it from the droplet surface where it is y naught to whatever its value far away from a droplet. Then we can integrate this parameter r from the radius, droplet radius, to some high value. So, by integrating this, we get this expression for the vapor mass flux, okay, which is equal to density times diffusion coefficient or diffusivity divided by r naught ln 1 plus this parameter, and this is known as mass transfer number, because this is basically the driving force behind the evaporation process. Okay. So, obviously higher this parameter, okay, then higher is the evaporation rate. How? So, if the value of y naught is higher, and let us say y infinity is fixed, and if y naught is higher, then this parameter is higher. Okay. But what can be the maximum value of y naught, or how do we know what is y naught? Y naught refers to the saturation condition. It is justified to assume that the droplet surface or the interface is always saturated. What does this mean? This means that if we go back to the example of water wave droplet in air, then at the interface, the amount of vapor that the air can hold is maximum for that temperature. So, how do we find what is the vapor mass fraction at the surface? By invoking Clausius-Clapeyron equation from thermodynamics. Okay. So, from there we can get the mass fraction, and from there we can obtain the from there we can get the mole fraction, and from there we get the mass fraction. Okay. However, for this you need to know what is the droplet temperature, then only you can find out the vapor mass fraction by that way. Okay. So, we have derived the expression for the mass flux. Now, this leads to some interesting results. Okay, let me first open. So, now let us first consider this. So, once we know what is G naught, we can multiply that with the surface area of the droplet to get the mass flow rate, or mass flow rate or mass flow rate of the vapor, or rate of change of droplet mass. And why we have a minus term here? Because in case of vaporization, always the mass reduces. Okay. And then we can also express the rate of change of mass by just expressing mass as density times the volume. And if we equate this, we will get an expression like this, that will tell us rate of change of particle size, like this. And then we can easily show that from here the rate of change of square of particle size is equal to this, which is a constant actually. And that is how we write that the d square by dt is equal to minus this constant kV, and this is what is d square law. So, you see, we have arrived at a very interesting and important result. What it tells us that the rate at which the surface area of the droplet changes, d square represents surface area, that is a constant. Okay. So, and that depends on mainly the diffusion coefficient, density of the droplet, and the mass transfer number, the transfer number. Okay. And now, once we know this, then we can simply integrate this equation from the initial particle size to 0. We are interested in vaporization time, this one. If you remember, we encountered this earlier, where? While deriving the mass coupling parameter. So, we compared the particle relaxation time with vaporization time of the particle to define the mass coupling parameter. So, what is vaporization time? It is the time that a droplet takes to completely vaporize, that is all. So, from d naught to 0. So, if we simply integrate this equation, we get that the vaporization time is equal to d square by kV, that is the evaporation constant. Now, this is also a very important result. See, we know that intuitively, we know that if we have a smaller droplet, then it will evaporate quickly. But what is the relation with particle size? That the quantitative relation is very important. So, here this tells us that it varies as d square, and this is the reason why fine atomization of a liquid is important in applications such as combustion, because we want the droplets to vaporize soon such that they can mix with air and start to burn. The burning process will take place only if the vaporization time is only if the droplet vaporizes and mixes, and that is the reason why the vaporization time is very important. And often in any phenomena, the vaporization time is much longer than the other time scales of the flow. For example, again if we consider combustion, then the droplets vaporize, the vapor mixes with air, then ignition takes place. Now, if you consider the time scale of different phenomena, droplet vaporization, time scale of mixing, that also requires some time, right? And then ignition and then flame propagation. For example, in a diesel engine, out of all this droplet vaporization time, the time scale of droplet vaporization is usually much longer. So, that is why the vaporization process governs the overall rate of combustion. Okay. Then, if you see, we have neglected any convective effect. Okay. We have made so many assumptions, but one of the key assumptions is that there is no convection around the droplet. However, we know that in all practical scenario, we have some relative velocity between the particles and the carrier phase. Okay. And how does that affect the evaporation process? Okay. Intuitively, you can think that if you have higher relative velocity, then the evaporation process should be promoted. Okay. So, for that purpose, here we rely on another model. I am not describing that model here. It is called film model, okay, where we consider that, okay, you have droplet here, and in the previous case, our vapor could go up to infinity theoretically. But now here we assume that if you have a convective flow, that condition is realized, or the location or the radius where vapor concentration is 0 is not at infinity, but at some other finite distance. So, this is, so basically you have a film around a droplet where you have the presence of vapor, and based on that it can be shown that still you have this form of diffusion dominated evaporation process. Only thing is that now the gradient is higher. So, the gradient between this, so this gradient what we have, earlier it was smaller because this change took place over a longer distance, but when you have convection, this change takes place over a shorter distance. That is why the gradient is higher, and this is the reason why evaporation. So, this is the physics behind the higher evaporation process that we realize in case of convection. Okay, and here it can be shown that the evaporation constant is modified by this term only, where this is known as the Sherwood number. It is a non-dimensional number. This is analogous to Nusselt number in heat transfer. That is, Nusselt number compare the convective effect to the conductive effect of heat transfer. So, in this case, this parameter compares the convective mass transfer to diffusive mass transfer. Okay. And this is expressed, there are different models, but according to this model, the Sherwood number can be expressed in terms of Reynolds number and Schmidt number, where Reynolds number definition you know. Schmidt number is the ratio of the momentum diffusivity to the mass diffusivity. Okay. And of course, this is limited to this range of these two numbers. But what it tells you that for if you have pure conduction case, then Sherwood number tends to 2 and this parameter becomes 1 basically. So, now we can use this modified form of the evaporation constant, okay, to derive the vaporization constant. Okay. And finally, we can show that the rate of change of mass transfer. So, ultimately what we want is an expression for rate of change of mass transfer, and now this is equal to minus G naught times 4 pi r square, and then if I plug in this value of G naught here, okay, and it can be shown that the mass transfer number or sorry the mass transfer rate is equal to diameter times this parameter. Okay. So, you see that the mass transfer rate or the rate at which the droplet mass reduces is proportional to size. Okay. It is directly proportional to size of the particle. So, here in this analysis we used size with this subscript d naught only to denote that it is the initial size, but we can conveniently replace this with just d, which represents the instantaneous size, and that is what is done here. And so, finally, we have this model for the droplet evaporation rate. Okay, so, we will stop here.